It's really a pleasure to welcome all of you here for this event. And before I start, I want to acknowledge two people that couldn't be with us today. The first one is Mario Ostendorf, the Vice Provost for Research, who helped us, put this event together, and unfortunately is on the East Coast, or fortunately for people interested in STEM and girls in research. She's doing an event there, and she very much cares about this. The second person that I wanted to acknowledge is Pradeep Fernandez, who is the Vice President for Strategy at Boeing Commercial Airplane. Pradeep is a member of the Innovation Roundtable, where he chairs the working group on next generation partnership. And this group was very important in the genesis of this event and putting it together. We have a lot of high expectation for this event, and we will articulate that in just a minute. I should mention that for those of you who do not know me, I am François Bonnex. I am the Vice Provost for Innovation and the Director of Commotion at the University of Washington. I'm also a faculty member in chemical engineering, where I lead a Energy Frontier Research Center. So I only do AI peripherally through my colleagues that understand the field better. But what we do have in this audience are practitioners of AI, and these practitioners come from different walks of life, including academia, industry, the startup world, and nonprofit. And we also have a number of administrators that are going to help us actually make the vision that we're hoping to catalyze today a reality. It's going to be an exciting time. I'm very much looking forward to the breakout session that will start at about 3 p.m. We're going to have 2 of them. But before that, we will have some context setting. And to start with, I would like to first introduce the president of the University of Washington, Anna-Marie Kelsey, who is going to open the festivities. Anna-Marie.
Thank you so much, Francois. And just to let people know, there will be more people trickling in. The Board of Deans, many members will be coming in, but they had a meeting on the other side of campus, so please excuse them for being a little bit late. It doesn't mean that they're not interested. Believe me, I'm sure that, it's almost impossible to escape conversations about AI. Some of them not very well informed, which is why it's so wonderful that we're getting together to really discuss an incredibly important topic. And I want to thank you all for contributing your time, talent, and energy to what really is a very important discussion. I'm excited to hear from our speakers, Ali Farhadi, and our moderators, Magda Balanzinska and Babak Parvis, and I'm sorry if I'm butchering your names, as well as our many panelists from UW and the private sector. This is really going to be a good set of discussions. And I think it's a real privilege for us to have this range of perspectives and experts here, and so that we can learn from this collected talent and wisdom. Like I say, there is a lot of conversation out there about this, like AI is going to, produce robots that are going to take over the world, or, et cetera. And it really is important for us to inform ourselves better. But there's also no question, I'm not, all that concerned about the robots, but there is no question that artificial intelligence represents a one-in-a-generation opportunity for real technological advancement and transformation. I was talking to someone who said that it's going to be the new electricity. And I'm not sure I'd put it that way, but I do think it will be pervasive in our lives, and that this doesn't happen all that often. This really is a once-in-a-generational experience. And it presents with us, with all the promise, we also have a profound responsibility to use these advances in ways that serve the common good, rather than perpetuating or exacerbating all the social ills that we are dealing with. AI, no question, has the capacity to create better, faster therapeutics, for example, to create new materials to help us with our climate crisis. And all kinds of things that I know a mere mortal like me hasn't even dreamed of. But if we're not careful, if we don't really reflect on its applications, it can perpetuate biases and be used for misinformation and create problems that we haven't dreamed of yet. Again, we as human beings are doing some of the work, and so our problems can become their problems and get magnified. We're very lucky, though, here in the Pacific Northwest, particularly here in the Puget Sound. We're home to many of the world's most talented innovators and world-class AI research, and here at the university and at our partner research institutions, as well as in public, nonprofit, and private sectors. As you can see on a day like today, we own the cloud here in Seattle in so many different ways, and that is actually essential to AI as well. So we are incredibly well positioned. And this is key because one of the things that we do exceptionally well in our community is collaborate. And the talent in this room demonstrates that, and that's what we want to really kind of give a kickstart as we look into the future, because things will be better, things will go quicker if we collaborate. And this is an incredibly exciting moment as we come together to plot a path for AI for UW in partnership with the organizations that are in this room today and maybe some of the ones that aren't here yet. And again, it embodies what we can do together when we put the public good first, because that's what it's all about, is how do we make life better for more people. We have a great agenda that will help us catalyze these efforts, and I'm eager to get to the meat of the conversation, so believe me, I'm going to step away. Very soon, we'll be hearing from Magda and her panel of UW AI experts about the many ways that researchers at University of Washington are approaching AI. Babak Parziv will moderate our industry panel to help us better understand what the private sector needs to be competitive and how the UW can play a role there. And these will be followed by brainstorming sessions in the afternoon so that we can get the different perspectives at the table and really, take our collective passion and, really magnify it. But first, it really is my great pleasure to introduce our keynote speaker, Ali Farhadi. He's CEO of the Allen Institute for AI, and I'm on the board, and we are so lucky that you said yes. We were thrilled that you came on. He's also a professor of computer science and engineering right here at the Allen School. And it really is very fitting that he represents both AI2 and the UW, which are both institutions that are very, very mission-driven. And because none of us can do this alone, we're building on that capacity for partnership and collaboration. Together, I really do believe that we can harness the power of AI to build a better world that's more equitable, sustainable, healthy, and prosperous for us all. But it's going to need all of us to put our wisdom and our passion together to make sure that happens. So thank you for being here, and a warm welcome to the CEO of AI2, Ali Farhadi.
Thank you. Thank you, Anna Marie. It's super exciting to be here. So what I'm going to talk about today is sort of my perspective on what's happening. I was debating myself whether I should just do a generic talk about the AI landscape or do a technical talk. So I sort of land somewhere in the middle. So I'm trying to anchor the few points that I would like to relay in the context of my own research. So my research lies right at the boundary of language and vision, and throughout my career at UW, I learned more about the role that interaction plays in our understanding. So my thinking has shaped around perception, language, and action and interaction. Also, what I'm going to talk about is shaped by my evolved way of thinking about impact as an entrepreneur, as a person who has actually shipped products in this space with a large number of users. So my way of thinking is actually a little skewed towards my understanding of what impact might actually look like in that space. So without further ado, so let me explain my weird title. What is the language model of a crow? So I thought that I would actually sort of anchor my beginning of this talk in the context of a long ongoing conversation around the role that we have about AI and the physical world. Almost 13 years ago, I was tasked by Paul Allen to set up a grand challenge in AI. So we put together a group of elite researchers and scientists around the topic. And this was the video, my running story in that talk. Little I knew about how AI is going to progress. But my point at that time was, look at this crow's deep understanding of what's happening in the environment around the crow. Excuse the bad quality of the video. I actually wanted to historically keep the video as it was. So there is this crow watching a fisherman in Arctic area digging a hole in the ice. So there's no fish, actually. So the crow didn't see any fish. But the crow knew exactly what to expect. She knew what the fisherman is doing. She knew exactly what to do, one after the other. And in a sequence of actions, masterfully executed one after the other to get to the goal that she wants. She knew what's on the other end of this rope without seeing anything about it. She knew if she actually pulled this rope, something interesting is in the other end. Look at her foot. So the way that actually, as she was pulling, she put her foot on top of the rope so it doesn't actually slide back. These very little subtle things are actually extremely fascinating. The crew knew exactly what she did to the fisherman. Because as he was actually walking back, the crew knew exactly what to do. I have to fly away. So this is sort of the level of understanding that I was actually advocating for many, many years ago as our way of thinking about intelligence. I'm excited about intelligence as it's defined in the word, physical word. And I wanted to sort of emphasize the notion that action, perception, and also our textual understanding goes hand in hand in this understanding. Well, what I wanted to do is now in the context of all these amazing advancements in AI that many of us wouldn't have predicted if you would have asked us 5-6 years ago, I wanted to sort of throw this as our favorite model. So I got the video and throw it at this multimodal large model of a few hundreds of billions of parameters. And look at the description that it gets. It's kind of amazing. If you would have asked me at that when I was presenting this early on, that could we get there? And with a deep voice, I would have said confidently, no, we need more time. And here we are. So this progress have surprised all of us, including many of us who are deep down in the details of the field. The results are phenomenal. We have some understanding of what's happening in this image, but I want you to look closely. Can I act on these understandings? These understandings are directionally great. They're actually amazing, but there are important pieces of this puzzle that are missing. Before the fish actually pops up here, no one knew it's actually fishing happening. There are subtle things like the shovel versus a stick. There is no notion of the whole activity. So stuff are missing, but it's actually fairly rich. So I wanted to grab this and obviously throw it at our new friend, GPT-4, and ask, imagine, given all this context, so expose all this context to GPT-4 and ask, now knowing all of these things, imagine you are a crow. What would you do? And the results are quite interesting. First of all, it's amazing that these systems generate those kind of things, but it's sort of at the abstract level. These models trained in abstraction on text, and they will stay in that abstraction. Sometimes they can extrapolate a little bit to the reality, but we need to be careful about it. So this is directionally makes sense. I'm a crow. I'm going to fly to that area because you mentioned that area. Generically, if I'm a crow, I get excited about shiny things. I get excited about food, and it sort of revolves around that way. Still not enough that I could execute on them. Not enough that we could build intelligent systems out there, but it's phenomenal. Now, I wanted to sort of ask the question that what can I do to build these large language models of the physical world? What is the language model of this crow? And apologies for the use of the language, I just wanted to stick to the terminology. What is the LLM of the world, of the physical world, of the crows of the worlds? And what do I need to build these models that perform that way? Among many other amazing things that went hand in hand to the progress in AI that gets to where they are, I would like to mention two things. And these two are, to me, are the most important elements. The first one was data. As the most element in the progress of recent AI advancements, I think data plays a key role. And the fact that we knew how to crawl the web, We knew how to get all the text in the web, organize them in the ginormous data sets of trillions of tokens. That was a key piece. And the moment that you manage to scale our algorithms so you actually can digest that volume of data, many phenomenal things happen. So one thing that I need to know is figure out how can I actually crawl the physical world, the way we crawl the web. The second piece is this magical loss function that we stumbled upon as we were training these models. Deep down at a very shallow surface level, the core loss function that we're optimizing is what is the next word. But phenomenal properties emerged from that loss function. Many of us wouldn't have predicted that we could actually do all these amazing reasoning capabilities, all these amazing actually emerging properties by just predicting what's the next word. So if I actually want to build this for the crow, what I need to find a solution for these two questions. How can I actually crawl the word so I can actually get data about it? And then what is that magical loss function as I'm thinking about embodiment, as I'm thinking about building these intelligent systems that can actually act intelligently in the world? And I'm going to spend a little bit of time today talking about a few snapshots of these things. It's an open-ended problem. By no means we know what to do here, but I'm going to sort of show some snapshots of what's possible. First of all, crawling the world. How can I actually sort of build this large-scale, corresponding large-scale data sets that we have for language for the physical world? Well, I'm not a roboticist, and while we're waiting for our roboticist friends to build us scalable, cheap, large-scale deployments of robots all over the globe so we can actually collect data, we are bound to other resources. And one of the things that we've been pushing for a while is what can we do with synthetic data? Back in a time, we built this environment called Thor, the House of Interaction. It's a synthetic environment designed by artists. Huge pushback against it in the literature. Texture is wrong. Animations are wrong. Physics are wrong. Your shadows are actually wrong. If you learn a model in this environment, rightfully, you won't be able to do anything in the real world because all of these things are not accurate to the real world. Fast forward 10 years. This is a most common practice in the space. We can learn a lot about in simulation, and we can actually find ways to extend them to simulation, to the real world. So one of the key things that we observed in language was scaling up results in interesting properties. We wanted to scale this up, but the issue is that every little piece of asset here is manually designed by an artist. And these are put together by artists or graphics designer. So this, by construction, was not scalable. So we need to find a way to procedurally generate, quote-unquote, unlimited amount of these kind of environments so we can start training models at scale. So if we built this thing called Proctor, Proctor is an automated way to build large number of houses of these forms, and that unlocked our progress towards building so many new properties at scale as a key part of this. So think about this as sort of our crippled way of crawling the world for now, to be able to actually sort of understand things, to be able to task these intelligent agents to start acting in the world as we're thinking about building these robust solutions, robust, safe solutions in the wild. So the same thing that we observed in language happened here. As we scaled more and time shows our size, good things happen. So we started a few years back at not being able to move around. And there are so many tasks that you could do in these environments. I just picked the simplest one, navigation. We task an agent go from point A to point B. Point B can be a semantic thing. Go to the fridge. Go grab an apple. And we were struggling quite heavily. And this is on an aggregate over the whole literature. This is not one single paper. These are the best papers or the best results across time. And over the years, we get really, really good at moving around. So now I think the latest results show something in the 90% success rate, but in moving around, trained in the synthetic environment, test in the synthetic environment. So now that we actually know somehow how to move around in synthetic environment, the next question was, well, so what? We wanted to actually move in the real world. So how can I actually sort of get these learnings and transfer them to real world movement? So I need to do a little bit of a detour here then. So one of the key phenomena that we got really familiar with and comfortable with as a whole nation was the notion of prompting. Prompting is a new thing for machine learning, right? We had train test, we were training our model, we freeze our model, we test them at test time, but now with prompting, we're actually providing context to the model, and somehow you could argue about it, but the model is actually learning while you're prompting. And prompting is a key to nudge the model towards the kind of context that you need to be able to perform the task. In my example, imagine you are a crow, blah, 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 and all the text around what you're seeing is a prompt to a model, explaining what's happening to the model. So if I want to deploy these models to real world, I need to find a way to prompt. But what is the correspondence of prompting in language when I go to the physical world? Well, one way to think about it, there are different ways to think about it. One way is to grab your favorite equipment of all time, your cell phone out of your pocket, and start providing a context. So think about this as actually you providing context to the model about what you need to do. With that way of prompting, now you can actually start providing context to these models. So you start to build your own structure of the environment. Then you can procedurally generate many, many samples for these agents. These are all different variations that you could speculate how this environment might look like given the prompt. And then you can actually throw it back at the algorithm and ask it to move around. So these are the first results that you could actually build fairly reliable agents that can move around in the real world while training them in the synthetic environment. So the numbers are actually phenomenal. There was a huge jump in our ability to move around. And this is the simplest task possible, moving from one point to another point. But still, it's a challenging problem. You need to reason about so many different things. You need to be careful about your empty space. You need to be careful about what's around you, how you can optimize your way around it. And as you go to bigger environments, you need to develop a notion of memory. I've been into this room before, and the fridge is not in that room. Let me actually try the other room. So there's a lot that you need to encode. But since it turns out that you could actually start moving around as sort of the very, very, very first small step in thinking through what we can do with the physical world, there are fundamental problems to be solved in that space. But now that I can actually start moving around, so moving around is just one of the things that we could do. I don't want to talk a lot about it, but you can actually start interacting with the environment, making things, breaking things. My favorite is you can actually train agents that learn to collaborate with each other. So now the same way that you and I can actually just carry both sides of the TV and move it around the room, these agents actually learn to expose the same set of behavior. The interesting piece, I'm not going to actually mention a lot in this space, but I will mention one thing because I want to connect it to the emerging properties that we talked about. So one of the things that we did, now that I could actually train agents to do things in this environment, was to task them to play a game against each other. Specifically, we sort of trained these agents to play hide and seek. Well, to be a little bit more accurate, it's a name called cache. Here's an object, here's an apple. Agent number one's task is to hide this apple somewhere, and agent number two task is go find that apple. Agent number one is going to be rewarded by how hard it is for agent number two to find it. Agent number two is rewarded by how quickly they can actually find this. And we let them play for millions and millions of hours, just playing against each other. Obviously, they learned how to play the game, and there are so many variants of that. I don't want to talk about that piece. The piece that I would like to talk about goes back in history almost 50 years. With psychologists in the room, I would like to keep this really at high level. So going back to Piaget and Piaget's stage of cognitive development. So this was sort of a big thing for us outside the field because they showed that infants can actually develop very, very early on, develop an understanding of the worlds around them that is really principled in an interesting way. They develop a notion of object permanence. Objects do exist. Things can contain each other. If I show you an apple and block your view, you don't expect to see an airplane coming out of that. You expect the apple to continue their path. And they had an interesting way of measuring their understanding by anchoring it based on infants' surprise. If I show an apple and the car comes out of the other way and infants get surprised, that means that there's actually something unusual happening. So we wanted to do the same thing. And these properties kind of emerged out of just playing a game of cache. Without us training these agents to get surprised or not about these tests were completely blind to the agents. But these agents show interesting properties that indicate that they also get surprised if an airplane comes on one side and then an apple goes on the other side. Or if one contains A, if A contains B and B cannot contain A, and things like that. So we tested these models, trained in simulation, by playing the loss function was just play the game. That's the only loss function you have. No other supervision of any kind. And they start emerging these kind of properties. I would like to connect it to the notion of emerging properties, these amazing properties that language models expose. And these are sort of another examples of things that are loosely related to that space, but interesting things are happening, going back to the notion that maybe there exists a loss function. We still don't know what it is. That if it's optimized for that loss function, interesting properties emerge. Now that I could actually sort of start acting and moving around in the world and collect data from the world, we need to index it. I would skip through this word because probably just the CS folks around the room would get excited about it. But if I want to actually understand the word, I need to learn a way to deal with hundreds of trillions of things around it. This chair is different from this chair. And if I'm actually acting in the word, I need to index it in a different way than this one. So that means that if you think about our neural networks that has millions of nodes, now I actually need to find a way to have trillions of nodes and more than that. And that exposes fundamental problems to us. And it turns out that if by being careful about log linearity in the binary code space, we can actually sort of start thinking about it. I don't believe that we're there yet, but we can actually sort of move in those directions. I think the latest results that we have that's actually already in production by Google is that you could start indexing 1 billion images, 1 billion, on only 8 gig of memory on your devices. By being careful about the log linearity of the label space. I would be happy to talk to you offline if you care about these topics, but I could now start thinking about moving around and indexing them. So I actually have these elements to start thinking about, can I start training these models? And as I start training these models, interesting things happen. It turned out that we were being naive about training these models because the way that we would train this would be drastically different from the way that we train our standard language models. The world is full of surprises. We have the notion of in-distribution and out-of-distributions, and many of those assumptions that we actually assumed for standard procedures won't apply here. We need to think about many principles that will change. I would like to mention a few of them as we're going through this. One of them is, what happens if I see a new thing? So what I'm showing to you is evaluation on standard benchmarks of the latest, greatest models out there. This specific one is a CLIP model by OpenAI. That shows that these models are actually doing phenomenally well. ImageNet is probably the biggest, hardest challenge, and they're outperforming anything else on ImageNet as a solution to that. These amazing models, when we showed them the data that was out of the distribution that they train on, naturally they don't perform as well. Sometimes they actually perform worse than chance. So we had, as a community, had to find a solution. I have these amazing models. They perform really well if it's in domain, and they actually perform poorly when it's out of domain. So people in the community sort of start developing algorithms that can nudge a pre-trained model towards a specific domain that you care about. Later on, we call them fine-tuning, and if you follow the space of language models, phenomenal stuff are happening in the space of fine-tuning, instruction tuning, self-instruct, including actually some of the stuff that folks at UW and AI2 are doing on Tulu and state-of-the-art models that are actually even performing close to GPT-4 numbers. So when you fine-tune, things get better. We celebrate it. Later on, we realize that, oops, when fine-tuned, things get better for the tasks that I care about, but I paid at the cost of other tasks. And this was actually a point of conversation that how can we start fine-tuning, nudging a model more towards what you're exposed at right now without causing damage to other things that the model have learned. Still an open debate on this, and there are phenomenal stuff are happening in this space. I would like to talk about one of them because that's sort of the simplest one and very effective. So what I'm showing is my target task. For a moment, imagine that all I care in the world is ImageNet results. And in y-axis is my control task. How well does it perform generally? If I have a pre-trained model, the star, these models are phenomenal. They're doing really great stuff. They expose certain characteristics in terms of how well they perform on the target task versus bench control. As I fine-tune, obviously my model is going to get better at the target task. Therefore, actually, the score is further down than the star on the x-axis, at the cost of coming lower on the y-axis, my control task. So how can I fix this? Very little detour. Imagine I have a model. This is my model. I'm actually showing you the loss landscape. Theta 0 is my initialization. I grab my data, I optimize my model, and I walk my way from theta 0 to theta 1. And that's the model that I've developed. The model is actually in the red area. It's a good model. I can actually celebrate and call it a day because now I am in a local optima and things are not moving further down the loss function. So I'm going to stop and say theta 1 is my model. There's a certain amount of uncertainty encoded in the way we train these models. If I actually try to do it again with a little bit of a perturbation, I arrive somewhere else. So I get my base model and I fine-tune it and I arrive at theta prime 1. So I have now two models, theta 1, theta prime 1. I spent a large amount of compute to get to theta 1 and theta prime 1. Lots of dollars are burned here. It turns out that if I actually look at the space between these things, phenomenal things happen. Many of them we still don't know. We have some hypotheses, some speculations, but many of these properties we still cannot explain in the solid theories around these problems. People have discovered that if I go between these 2 points, literally I get theta 1, theta 2, get the average point. That point is not a model, right? I just average 2 points in higher dimensional space. It turned out that that point is actually a model. I could grab that point and treat it as a model that I've trained. That was a big surprise by itself. But it turns out that because of the properties and the way we optimize these, that middle point is a model by itself. But it didn't stop there. That little point is a model that can actually be better than the model that we optimized for because of the SGD and all the optimizers we use. So that score and this scores are two different fine-tuned versions of the model that we trained. And look at the line between them. Many points that you pick on the line between them correspond to a point that is better than any of the optimized points. And these are the points that we cannot get at by using the optimizers that we have. So if I want to trace out that line, here's the curve. We stared at these curves for a long time because we couldn't explain our way out of them. You have a pre-trained model, you have a fine-tuned model, and I walk my way from one to the other, and I arrive at a point. Look at the blue one. This point is more robust than my pre-trained model on control tasks, and is slightly more accurate than my fine-tuned model on the target task. Right? All I'm doing is simple arithmetic between two models. I'm not even training a new model. And that's sort of an interesting property. That got us to sort of putting all of these models together, form a big ensemble, and sort of this was a UW submission to the ImageNet challenge. And this is actually sort of a big deal challenge for people who participate in image understanding. And UW was actually sort of the winning submission because of these properties. Once we patched, things got better, obviously, and now with all the other domains, so we can actually inject robustness to these models without losing the accuracy. And if you think about it, we started developing a notion that now I can actually start interpolating between two models. Now we're walking into the space of simple arithmetic between models. Right? These are the things that I've trained with weird algorithms that I cannot even explain. And now I'm actually talking about operations in the space of them. So now I started talking about interpolation. Let me ask you a question. Can I also extrapolate? What does it mean to extrapolate one model from the other? So if I have two models, I interpolate, I get something that is a mix of the both of them with interesting properties. But what if I actually move the other way? While we're thinking, let me introduce a notion. So I'm going to introduce a notion called task vector as I'm starting to establish arithmetics in the space of models. The task vector is a vector, literally a vector, that gets me from theta 0 from a pre-trained model to a fine-tuned model. Think about it as a vector in a very, very high-dimensional space. So if I have that vector, now I can start thinking about negating tasks from each other, adding tasks together, and many other simple arithmetic between the space of models. What does it mean to negate a task from another? You're going to start unlearning. We all talk about toxicity encoded in these language models because it's just in the data and the models exacerbate the situation. But can I actually get a toxicity model and negate it from an actual LLM? What would happen? Well, it's actually interesting. Look at the green dots as I'm actually extrapolating one from the other. So I'm not moving a lot in this direction, meaning actually I'm maintaining the quality of the original language model while making it way less toxic. We talked about putting models together. Right now can actually start ensembling models, but in a free way. When we think about model ensembling, oftentimes I have to run multiple models, get the aggregate information. But now what I'm saying is that you can actually ensemble models by just summing them computationally free. And you still have one model that acts as an ensemble. There are a lot more that you can actually do in this space. But with the way that this whole industry is evolving, I would speculate that we would be spending a lot of our time instead of training new models by just figuring out what to do with the large pool of already trained big models. So what I'm showing you, this is time, the number of models with a shared backbone on Hugging Face. The space is exploding, meaning that many people might have probably trained a model that is going to serve me. So instead of me training those models, I might be able to just grab them and sum them with some other things to get to the point that I would like to do. And one hypothesis, and this is not proof, this is just a pure hypothesis, is that I really hope that we spend a lot of our compute and thinking instead of training a model from ground zero for my own task to figuring out what's already out there. And there might be interesting things for me already out there, and I need little data, maybe a little compute to be able to get there. But that's just an unproved hypothesis. Let me talk about another property that happens when you start thinking about a real world. We all remember preparing for exams. For some of us, long time ago. For some, not a long time ago. Or as we walk into a meeting, people would brief us about what's going to happen in that meeting. So those small amounts are quite effective, right? In the light literature, again, I don't want to actually walk into the actual technical literature as I'm clueless about that topic. But neural priming is a thing in psychology. People actually get primed and the results get changed. But naively thinking about priming, can I do the same with my model? Can I actually, before going to the exam, can I teach a little bit about what you're expecting to get to the model, obviously not showing the actual test? So this is contrary to what we teach in machine learning, right? We spend a lot of time saying, do not overfit, do not overfit. Make sure that you're not overfitting to the test set. So what I'm saying is that, can I actually overfit at test time and discard it? The same way that you get prepped for a meeting, you walk into a meeting, and all this stuff evaporates. But your performance in the exam, in the meeting, would be drastically different with and without priming. So here's the test. I'm going to grab your favorite choice of model, and you show me a query and ask, what is this model? What is this picture, let's say? I don't know the label, so I'm not cheating. But I'm going to go in my train set, fetch images that I've already observed and train on, and fine-tune on them in an unsupervised way for just a tiny bit. So no new data. This is actually a data that I was used during my pre-training. I've seen it before. It's not a new thing similar to the exam. It's not a new topic. You've seen it before in the class, but you're just priming your brain about it. So you can actually start doing the same thing. Provide your instance to the model. Use that instance to fetch other things that you have seen before. We're not using any label data. Then nudge your model a little bit, and now perform your task. And all that happens on the fly. Huge things happen. So this is sort of a state-of-the-art OpenAI CLIP model, and this is the primed version of that. No new data, no new supervised algorithm, no new model. All we're doing is that at inference time, we're just nudging the model towards the distribution that you care about in an interesting way. And there's so many details about it, but this gap is huge. Oftentimes we celebrate if we get 10% improvement on any of these algorithms. So suggest that as we actually start thinking about embodiment and putting things out there as they are behaving in the real world, and world is dynamic, is a dynamic thing. We should expect change. We should expect unseen elements. So we need to bake those into the algorithms as we're developing embodiment. Last piece that I would like to talk about in terms of what properties that we want is the notion of not all tasks are equally hard. Not a surprise to people. But the way that we treat them with these big models is that we actually sort of run the same model for every task because we don't know what is hard, what is not. And there's an interesting piece that you could encode a sort of a nested architecture as part of your representation. So you bake in one model, still one model, but you train it in a way that at inference time, when you want to use these models, you can just grab the chunk that you care about. And you don't need to specify how big the chunk is. But you can train it in a way that these chunks behave similarly. And as you grab chunks, the results don't degrade drastically. Obviously, the more you have, the more capacity you have, the better you get. But you can actually start building these models in a way that you could serve the simple ones with the small one without the need to go bigger. So we call these models Matryoshka representations because of the Matryoshka dolls that go one inside the other. And then you expand it to sort of standard models. Now the beauty of this is that we're now moving from the notion that model is a frozen thing, you train it and then you use it, to model being a fluid thing. Because now you can actually train a model, but serve thousands of models. So those little triangles, red ones, are the models that are trained independently for different capacities, for language and for vision. And the dots, the star ones, are different chunks that you could grab at the same time. So notice that for the cost of training, I'm actually training 4 times the cost. Versus the cost of training here is just slightly more than 1 time training. But now you actually have this fluid structure that you could grab whatever you want out of it at inference time with consistencies being baked into the way we construct the model. If you were not recording live, I would have said that this model is actually now becoming the backbone of some of the big models that we heard about, or we will hear about in the industry. So interesting stuff. I would like to talk a little bit about some of the challenges that we're facing as we're thinking about AI. So I think it's an interesting time in AI. I don't need to spend a lot of time arguing about a lot of good progress. A lot of things are happening. Now we actually have this tool, to some extent semi-baked tool, to some extent a really good, powerful tool that could help us in doing whatever we want to do in our science. And this is actually a powerful tool. It will become a standard tool across practices. I think Anna-Maria was talking about climate and the role that AI is already playing in climate. And there's a lot more that can be done. If you have seen David's talk, any of them, you would see actually how AI plays a role in protein structures and cell structures and all of those things. There's a lot that's going to happen in this. And I think these tools will play a significant role across the board. But there are major problems. One of them is that if I look under the hood, and what do I need to be able to move the needle in some of these important problems? Well, I need my AI tools to work. I need the right set of domain scientists to actually know how to solve the problem. I need the infrastructure. I need the training data. And I need the compute. To me, we are OK in many of these parts, with the exception of one important bottleneck. And if compute is not there, I don't know what we're doing. So this is the oxygen, the existential crisis that we're in right now. And the gap between people who have compute and people who don't have compute is just widening really fast. So I would like to repeat myself that without this, we don't know what we're doing. Sort of what would we do as AI researchers? What would we do as scientists in this space? So the compute is actually sort of the crisis that we're in. This gap is getting wider, but also recovering from this gap is also getting harder and harder by day. The costs of GPUs are climbing every other week. And as demand goes up much faster than supply, we're pretty much guaranteed that for a while, this is what we're fighting against. And this is the kind of problem that none of us can solve by itself. Anna Maria was talking about no one can solve these problems by themselves. It's a partnership problem. But also it's a problem that will get resolved, in my opinion, from a top-down approach. Because there is a chicken and egg problem. If I don't have the compute, I cannot contribute. If I don't contribute, I cannot get the compute. So I'm actually asking from a top-down investments on compute, because otherwise the gap is widening. What makes it worse is that it's just getting hard by day to just close the gap and arrive at the same gap that you had before. So this would be an existential problem, in my opinion, and we need to think about it very, very carefully as we're thinking about what does it mean to actually do research and science breakthroughs. The other piece that I would like to talk about is the way that the field is evolving and the key role that we have to play in this space. In my opinion, AI was developed in open. I use the terminology, AI is actually born and raised open. Last year or so, it's getting extremely closed. To me, we talked about the problems and we need to be careful about AI safety. The biggest problem to AI and AI safety is the closed nature of the problem. And we are at AI2, we're all in for this notion of we need to open up as much as we can to be able to assure transparency, safety, trustworthiness about AI. And there's a whole spectrum when we talk about openness in AI. Sometimes I train a model behind a closed door and toss it over the fence and say, this is an open model, use it. Great, this is actually a good movement towards the right direction, but that's not enough. I cannot evaluate a closed model. I cannot evaluate the behavior of your model and establish a relationship between the input and an output if you don't expose your training data, if you don't expose your training algorithm. All this progress happened because all of these were open. And suddenly we're closing up, and I'm actually deeply concerned about it. So one of the things that we started doing is, let's start opening the data. No one is incentivized to open the data set. It's expensive to build it. It's one of the key elements. There's a lot of know-how goes into how you get your data, how to curate it, how to filter it, how you train on it. So we started putting things out there in this space. So the very first thing we did was actually release a 3 trillion token data set for people to start using it. And the adoption was phenomenal. So you have to sit for 3 days on a terminal to download this. But many, many people started downloading it. It just speaks to the volume of a need, the necessity that all of us see that if I actually have an open data set that is carefully curated, PII doesn't exist there, sensitive information doesn't exist there, a lot can happen out of that. Our next step is around actually sort of releasing our models, and we're trying our best by figuring out all sort of partnerships to get our hands on any kind of compute that anyone has across the globe so we can actually start moving these models forward in partnership with others. We need a lot of compute, and they do not exist in one chunk anywhere. So partnerships, openness, and being able to actually sort of think about public-private relationships is actually a key piece of the puzzle, in my opinion, to be able to get the resources to do the right thing. And as I said, I'm worried about the closed nature of AI. AI was born and raised in the open, and keeping it closed behind the door caused one problem. And that problem is that it would actually hinder and block the progress. And progress is the key thing that we need to actually ensure safety in AI. We see a lot of hypes and noise in AI. Oh my God, it's going to wake up tomorrow and kill us all, and all that story. But the real problem that will cause trouble for us is just the closed practice of AI. And if we cannot find a way to open this up, major things can happen. And I'm really worried about a future where Open communities cannot actually get close to the closed approaches, and researchers won't be able to perform the task that they need to do. So there is a compute crisis, there is a closeness crisis, and I think they are tied together in a chicken and egg way. I actually would like to quote Tom Mitchell, ex-dean of CMU College of Computing. We talked 3-4 months ago, and the point he raised was actually sort of an interesting point. He said, we spend a lot of time preparing these amazing world-class scientists to be the people they are today. These are the faculty who are doing research on these areas. But now they're coming back to my office asking, what do I do now? I'm ready to help, but I cannot help. So the cost and the damage of us having these amazing people, but not empowering them to do the thing that they're trained for, is actually bothering me a lot. And we are in this situation across the nation. Some people speak, some people don't speak. So compute and openness are two biggest problems that we're facing. And I believe that we need to have a systematic solution to the problem. Something that actually starts from a top-down approach and then moves to a bottom-up approach at some point. And I would end with this, that if there are technology gaps, as I was trying to allude during my talk, these technologies by no means are ready to say, oh, we're done with these technologies, let's go actually do other things. The problems that we talk about on safety, transparency, the solution to those problems these are technological problems. And we have the people who can actually work on them, but they just don't have the right tools. And if we would like to close that gap, we need to open. And with that, I stop. I would be happy to take questions. Thank you one more time, Anna-Marie, Francois, everybody else for having me here. It was a pleasure to be here.
Fantastic talk, and I completely agree with your points at the end. I just wanted to, something that I've seen in my area is a little bit, I think is critically dangerous, is that there's been a lot of calls, and you alluded to this, there's been a lot of calls for safety. There's been a lot of calls for safety in AI, and I think there's a real danger, and that's happening now, that private companies will use safety as a pretext for not being open. And I think that really has to be fought at every stage because it's very, very dangerous for all the reasons that you've said. So, there's obviously openness is obviously a good thing, but if now the world, particularly the private part of the real world, has a kind of a seemingly ethical motivation for not sharing, I think it gets very, very dangerous. So, and I think the best way, like you said, to combat to deal with dangers is by being completely open. So I think everyone who's in decision-making place should really be thinking about that, from journals everywhere else. Yeah.
This is an excellent point. I completely agree. I think that is a big threat. Closing up, so we are actually sort of doing this op-ed piece, which is exactly the point you're making, that close and safe are not synonyms. To some extent, they're actually opposites. We would not be able to, and there's good reasons, right? There are these technologies, they have the potential to make a lot of revenue, and there's not much moat around these technologies. They're actually reproducible. What do I do if I have one of those? I have to hype it up. Oh my God, it's so dangerous, no one touches it, only me. And that is a running story around in DC, in Capitol Hill, in White House, and we're fighting that in every moment that we have. So the unfortunate piece is I actually had to travel to DC 4 times in the last month or so for that very same reason. I actually really ask everybody, please do that. We need more people to speak up. We need experts to speak up that, A, these are technologies. It's a language model. It's not going to wake up tomorrow and do anything about it. And yes, these are powerful technologies. And like any other technology, as simple as a knife all the way to a language model, people can use it in a bad way. But we need to be prepared for that. And the preparation for that is not through closing it up. Let me pause over here. I'll be happy to actually dive deeper. But I'm actually super happy to see that this is actually the same viewpoint across the field. It's a big danger. And if we don't act on it in a proactive way, we will end up in a situation that we are fighting some policies that are already ruled out.
Fantastic talk. I wanted to kind of ask about how you're centering compute as the bottleneck in the face of other advancements. I think with a lot of people were sort of worried maybe a year ago that it's like, boy, we're all going to have to study these handful of foundation models and everything else that just can't even possibly compete. But there's been some good news over the last year, including some of your work, where it says, there are ways to kind of achieve competitiveness through various fine-tuning schemes and LoRa and quantization and everything else. And then especially maybe the work you talked about where, kind of algebraic combinations of models perhaps gives you ways to do anything. So doesn't that kind of help combat the dependency on having a farm of 1,000 GPUs? Should I be pessimistic or optimistic about the outlook?
That's a great point. Let me rephrase it the following way. So yes, these models are getting bigger and exposing interesting properties. At the same time, we're seeing sporadic evidence that the smaller models can do something interesting for some tasks. These are not established. I actually play that game a lot myself. I spend a lot of my time thinking about efficiency and how to run these models. But I do argue that we still don't see anything nearby. If we want the capabilities that we're excited about, at the moment they reside in the bigger side, unfortunately. Maybe there is a magical moment in the future where we discover something, but even that process, the process of discovering that, it's a large-scale effort by itself. I might end up at a small model, and after that point, things get better. But to me, to arrive at that small model, I need to run large-scale training. Sometimes even more than the bigger ones, because I need to squeeze everything out of a model. So because of that, I cannot think of a major problems that we're facing right now that I can solve without major compute resources. And that imposes unfortunate weird dynamics now. The gap is widening, and I'm worried about that gap. And I think it's on us to act. And places like Seattle were really well suited to act on this if we get our act together.
So I have a question about there's two existential problems that you're talking about. One is access and sort of equality to compute, obviously, and then the culture of kind of openness and transparency and the safety elements that come out of that. And so when you talk about a systematic top-down solution, can you comment, in your opinion, on sort of what the process to get there is and where we're trying to go?
Short answer is, I wish I knew. Slightly longer answer, here's the reason that I have. I don't think we need to have the basis. We just need few large state-of-the-art, scientifically developed by scientists models. And then you can start driving off of those. To get to those base models, we have two alternatives. Big enough institutions can start acting and start organizing their behavior around it. We're seeing some sporadic evidence that things are happening. For example, President's EO was one of those, and NAIR is an example of those. It's a national AI research initiative. We're heavily involved in that. We're trying to shape up what it means. But at the bulk of it is Biden telling the cloud providers, cough up some compute, get people like us, train a model, and expose it to everybody. So that's one possibility. But even at the level of the president, their issue is that they cannot get enough funding to do this because there are more important stuff happening in the Capitol. But below that level, even at the university level, by just being careful about and strategic about what we're doing, we can actually move the needle much faster in the right direction. Hayek, there are good stuff are happening with Hayek, for example. There are more GPUs being added. We're thinking about modernizing it and all that jazz. But I think we just need to act faster, because the cost of recovery is also increases dramatically, aside from just the cap.
So I'm actually very concerned by the fact that while our field is moving towards more and more openness, actually the field of bioethicists and ethics field is actually moving 180 degree, and they're actually advocating for more controlled access. And I think this exponential success of large language model really hurt us, because now people are scared. And then even with the EO, just talking about trustworthy, safe AI, I think the public just really needs to be educated more on what are the pros and cons and what we are weighing against. And then as a field, I think we really need to be more vocal about what that means for the public safety.
You touched upon a few very important points. Let me actually sort of go through them one by one. One of them is that, yes, it's actually a major concern that people who have been trained as people who need to care about safety are panicking. part of it, thinking through the problem through their lens, they have all the rights to panic. And when they panic, what is the right tool? What is the right reaction? Let me actually close it up till I figure out what to do with this. So part of it is just natural, the way it has evolved. It's dangerous and it's worrisome and we need to act on it. Now, how can we fight that? So one is sort of relax this notion that closing it up won't make it safer. And there are few things that we talk about and argue about. One is that, well, a technology as widespread as these models are, you cannot confine it. Like even people use the nuclear weapons as an example of a success for confining things. And I would argue the other way around, is that the fact that you actually have to impose so many sanctions just suggests that you cannot confine a technology, it will leak out. The other argument that I make oftentimes is that the cat is out of the bag. There was a point in time that we believed that there's only a handful of entities who could train these models, and oh my God, this is so magical that no one else can train it. Fast forward 6 months, there are like dozens of them out there. And if you wait another year, there's going to be hundreds of them out there across disciplines. So that's the second argument. The third piece, which is actually to me the most important piece, is that people get comfortable with these things, even regulators and ethicists, in two scenarios. One, if they can actually understand and interpret these models. It's hard and I don't know how to do it. It's an active area of research, not mature enough to be involved as part of policy. But there's another part to it. People get more comfortable if they can trust. And people trust if there exists an evaluation out there. Right? The phone in front of you, you cannot interpret, probably if you're not in that space, you won't be able to interpret those things. That phone makes a lot of decisions at every moment for you. You just trust it. Mainly because somebody evaluated the behavior and you now trust the behavior of those things. So one of the things that we are arguing really strongly for is if we start putting in thorough scientific evaluation in place, that would relax the community a little bit. And that's a hard, open problem by itself, right? We honestly don't know how to evaluate these language models to begin with. The metrics that we have are not as strong as we would hope for. The benchmarks that we have are already in the training set of some of the other algorithms. And there are certain behaviors of these models that we're not even evaluating. So I think the very first piece of the puzzle that I believe, again, it's an expensive, hard challenge, but that's what we're trying to do, is can we put out thorough evaluation out there for everybody to start seeing the behavior of these things. And that connects to my last piece that you pointed out, that as people start learning about how these models are expected to behave under different scenarios, then they have a better educated guess. And I think there is a gap in AI literacy. And at least for that one, we're really well suited to act on it. Policymakers are living in a whole different world. I had the unfortunate time of actually spending a lot of time with them, and their mindset is actually somewhere else. We need to get them back to the reality. So general public reads this PR, and these PR machines are fairly strong and fairly powerful. We need to start acting in the opposite direction and talk science out of these hypes. So put into place evaluation, literacy, and also all of us actually sort of starting talking out. I'm hopeful that we should be able to start getting more of the people who are concerned for the right reason about the consequence of powerful technologies to a little bit more ease.
All right, thank you very much.